Good morning, everyone. This is Heather Smith at the Michigan Concrete Association. Thank you for joining us for the Portland Limestone Cement webinar that we will be doing today. We would like to welcome our speakers, Claude Bergeron from Wholesome. He's a technical services engineer, and Dan DeGraff, our director here at the Michigan Concrete Association. We're going to be talking a little bit about Portland Limestone Cement, making the transition, adjusting your specifications, and why we're doing it here in Michigan. So a little bit of housekeeping items for today. If you have any questions, please put them in the chat. We'll do our best to hit those as we speak, but we might hold some of them till the end. You will receive an hour or an hour and a half, depending on how long we go, continuing education hours for this webinar. They'll be emailed to you following the webinar. Give me about 24 hours to get those out. And again, our information will be on here. I'll put our information in the chat and our website where we'll be hosting this webinar. We are recording it. We will be hosting it on our Portland Limestone Cement page so that if you need to share this with others, it will be available on YouTube and a link to share. So without further ado, we will get going. Again, I'd like to introduce Claude Bergeron from Wholesome. He's, again, the technical services engineer, and he's going to talk about transitioning from type 1 to type 1L from the cement manufacturer side. And then we will have Dan DeGraff follow up with that. So without further ado, Claude, go ahead.
Good to you. Great, thanks, Heather. First off, I want to thank the MCA for inviting me to speak today. I appreciate the opportunity, and so let's get at it. Oh, didn't click. Uh-oh, there we go. Seems going to be a little bit slow, I think. But so today's presentation, it's a presentation about understanding the cement industry's response to CO2 and in the cement industry's attempt to just become more sustainable. Certainly, the cement industry, we understand our role and in the environment, and we're certainly going to, you'll see here, do our best to improve our role as far as sustainability goes. I guess the question would be like, why are we headed in this direction? And I guess I would say, it's not just the cement industry; it's the whole concrete industry in general. And for the most part, if you have your ear to the to what's going on in the news, you can see here there's some examples. Concrete, the most destructive material on the earth, things like that. I literally heard on the radio just 2 days ago, some studies just came out regarding CO2 levels, and so I literally just printed these this morning. For example, again, this is just from 2 days ago. CO2 level just passed an important benchmark, a measure of humanity's war on nature. That's that headline. Another headline, carbon dioxide levels in the atmosphere are highest in history. And there's tons of them. There was another story here. Aerosols from burning fossil fuels are masking global warming. And with this one, they naturally they have a large aerial photo of a cement plant. So I guess the point is simply that, yeah, it's it's real. It's folks who are in the concrete industry, we're certainly in the crosshairs. I guess I would say not only cement plants and cement companies, but all of the other allied industries, whether it's aggregate, admixtures, the people who mix them all together, and whether it's whether we're building roads and bridges or residential driveways, the reality is we are all kind of connected at the hip. And I'll go as far as to say even the design community. If you are designing with concrete, then certainly this is something that we all need to be aware of. So I guess the question would become, well, why do we need to be aware of what's really going on with this CO2 discussion? Well, what's happening at a cement plant is, and we'll talk about it, but as we produce clinker, which is the product that we're going to eventually turn into Portland cement, we produce CO2 at our plants. And CO2 has been identified as a greenhouse gas that traps heat and radiation in the atmosphere, which then warms the surface of the earth. So it's this whole idea of this greenhouse gas that we produce at our plants and warming the surface of the earth, that is the real concern, right? So I just mentioned that we make clinker. And here's a picture of you can see here, these looks kind of like a bunch of burnt up little marbles, if you will. Well, for every 1 ton of clinker that we produce approximately 1 ton of CO2. And just to give you some examples here, you can see that in the United States, in 2020, it was estimated that cement plants produced 90 million metric tons of clinker, therefore producing approximately 90 million metric tons of CO2. You can see there the world, though, overall, making 4.1 billion metric tons of clinker. And you can see there, with China leading the race there at 2.2 billion, and again, India at 340 million. So the point is, cement plants produce clinker, and as we produce clinker, we produce CO2. Just to kind of bring it home, I know I try to keep this as a very generic presentation, but since this is Michigan, I can tell you that we have a plant in Alpena, for example, which makes about 2 million tons of clinker. And so therefore, you can say in Alpena, it's we certainly don't want to make 2 million tons of CO2. So that's kind of just kind of gives you an idea of what we're talking about. So kind of moving along, I want to kind of put that aside for a minute. I talked about a lot of different topics to get started, and hopefully I'll kind of bring it all together. There's a movement in place called the Buy Clean movement. And what that is, it's an idea found in both public and private sector as an effort to reduce the carbon footprint of products and buildings and things like that. So there's this idea of a Buy Clean movement that is taking place. So more specifically, what we see then are what we call Buy Clean policies. And we see these at not only the federal and the state level, but we're even seeing some of these Buy Clean policies at the local level. And to kind of give you an example, these policies are written in what's called the Clean Futures Act. And we'll talk about that in a minute. But the point of these slides here is, the idea that, the thought process is, legislation that encourages, cleaner materials, right? As far as CO2 output and things like that. To draw your attention to this map of the United States here, you can see I have some states that are kind of colored in light yellow, and those are states that are considering Buy Clean legislation, right? And I think there's even a few more, and I've even heard some talking, in Michigan as well. But these are states that the legislation has actually been introduced. Now, I'm not sure where they are as far as passing it, but it's certainly been introduced at their state level, and even at some of them at their local level. Now, California, for example, they already have Buy Clean legislation already passed. Now, what's interesting about this little map is, at the end of a presentation, you always have to show some pictures of completed projects with the new cement, if you will, for lack of a better word. And as you can imagine, the majority of the pictures I'm going to show you are going to be from like Texas and Colorado and Washington and that kind of thing. Again, I try to keep it as a generic presentation, but Wholesome, we operate plants in these states as well, and I can tell you that these states have transitioned over to a Portland limestone cement probably about 5 years ago. At least they were they were ahead of us simply because, quite frankly, they had to be, because they had legislation on the books, right? So now I mentioned this Clean Future Act, and so what is this? Our current Congress, put together this act. And it's also known, you can see there, as the Leadership and Environmental Action of Our Nation's Future. Okay, so and what this is it's legislation which creates requirements and incentives to reduce emissions of greenhouse gases. And they establish some goals and so forth that every federal agency must develop a plan on how it's going to address this Clean Future Act. So again, if you're going to be supplying materials and do government work, well, you're certainly going to need to be aware of this. And in large companies, they take notice of this, and and we try to be prepared for it. So anyway, so that's kind of the idea of or kind of a little bit of the thought process why some of this is happening, quite frankly. Here you can see this would be at the again at the government level. Here you can see we have this concrete expert. Arnold Schwarzenegger saying cement factories said there is no way to produce cement without polluting the way we do now. And we found that there are many European companies producing cement that release only half the greenhouse gas. So the technology is there. So what technology is he talking about? Well, he's kind of talking about, even though he may not know it, he's talking about the idea of a Portland limestone cement. Okay. And this you can see is going back to 2007. The idea of a Portland limestone cement, Europe's been doing this for many years. Canada has been making Portland limestone cements for probably a dozen years or so. So the technology is there, and like I said, we are just now introducing it, and that's kind of what this presentation is all about, right? And then that's at the government, perspective. And then, like I mentioned, the Buy Clean movement. It's a movement also at the private sector as well. And you can see here another concrete expert, and his comment: "I'm optimistic that innovation can help reduce the downsides of concrete. Researchers are developing new materials that would cut down on our need for concrete in the first place." Which I think is an absolutely foolish comment. Cement, for example, is the second most used material the world over. It's second to water. Okay, so I think concrete is going to be around an awful long time, and but certainly both in the private and public sector, we need to rethink how we are producing our cement. Which again is what really the direction of where we're headed, right? So okay, this is just kind of an interesting slide. We do not have a carbon tax in the United States, but I just want to give you kind of a snapshot of some other countries. Now you can see here Canada, which here in Michigan is certainly our neighbor, but as close as British Columbia, with a 20, and this dates back to 2018. So this is actually kind of an old slide, but $27 tax on carbon. So if you consider the fact that I kind of mentioned earlier that our plant in Alpena producing 2 million tons of clinker, $27 times 2 is 27 times 2 is 54. So can you imagine paying $54 million in a tax? And I know I saw recently that Canada has some goals to increase their some carbon taxes, and so these are just things that companies look at. Certainly most cement companies are rather large and they work in numerous countries. My company is European owned as well. And so these are things that are certainly on everyone's radar at the cement level and the concrete level in general, right? So now I want to introduce the idea of something called global warming potential. referred to as the GWP. So what is a global warming potential? Well, this is a metric where the abilities of different gases, the different gases' ability to absorb heat is normalized to a CO2 equivalent. Okay, and it's represented in metric tons of CO2 per kilogram of the gas being evaluated. Okay, so what we can do is we can take products and we can kind of put some science to it now. I think a lot of times when we were dealing with lead and many years ago, there was a lot of greenwashing going on, right? And there was it seems like things were kind of vague and a little slippery, right? Well, now we're in a situation where we're trying to put some real value to numbers to what we're doing. You may say, well, what do these numbers mean? Well, the industry average for type 1, the Portland Cement Association did a study, and they came up with, with that. Well, you can see the value right there, 922. So what does that mean? Is that good? Is that bad? It's just a value, is what it really is. It's just the value of the average industry for type 1. But the idea would be, how can we lower that number? So everything that a cement company is going to be interested in is, what can we do to improve our global warming potential? And then that's a lot of what we're what we're really aiming at doing, quite frankly. Okay, so I mentioned a little bit earlier, I kind of tried to set the stage about CO2, and now I've kind of mentioned the idea that we want to lower our GWP. So what's going on at a cement plant? I talked about clinker and everything, but I was kind of quick and vague. So what are we really doing at a cement plant? Well, during the manufacture of cement, limestone and selected raw materials are crushed and milled and proportioned and in a manner that the resulting mixture contains the desired chemical composition that we're looking for in the finished cement. Okay. And all this material is then fed into a kiln, and the kiln is fueled by fossil fuels. And the fossil fuels are then heated to approximately 3,000 degrees Fahrenheit. So we introduce, I don't know if you could, I think you can kind of change my pointer here, but so we introduce ground limestone and clay at one end of the kiln. At the other end of the kiln, we have our flame, going. And then out of the kiln comes that clinker, or the clinker is what we ultimately are going to eventually grind into our cement. So then the problem, I don't want to say a problem, but for lack of a better word, what comes out this kiln is our CO2. Okay, so you can see here the burning of this material is termed calcination, and that emits approximately 75% of the CO2 that a plant emits. Okay. So this is what really kind of is the I don't want to say the issue, but this is the crux of what we're talking about. Creating this hot air to burn up the limestone to create the clinker that creates our CO2. Okay. So the idea would be, any attempt made to reduce the amount of material fed into the kiln will reduce your CO2 emissions at a plant. So what I'm getting at is if we ultimately want to produce this clinker, this product right here. However, if we can put less material through this kiln, we're gonna produce less CO2. So if you follow me there, what I'm getting at is, here's our 1 ton of Portland cement clinker. Let's say we take 5% of this Portland, or I'm sorry, of the cement clinker. If we took 5% of that clinker out and only made 95% clinker, and then put, say, like 5% ground limestone into that 1 ton. So let's say we marketed to the concrete producer a product that it's still 1 ton of cement, but it's 95% clinker, 5% ground limestone, and we market that to the producer, and he makes his concrete. What do we just do? Well, we've saved 5% of the CO2 at that plant. So in Alpena, for example, if we were making 2 million tons of clinker, you just reduced your CO2 output by 5%. Now it's a small number, but that's exactly what we've been doing for probably about 10 years, maybe a dozen years now. So what does this mean with respect to cement specifications? It means that ASTM C150 for again, I kind of forget now, but for 10 plus years or so, has allowed 5% of ground limestone to be introduced into that 1 ton of clinker. So you can see right here, limestone, the amount shall not be more than 5%. So by doing that, we've been able to reduce the CO2 output at our plants by 5%. You make 2 million tons, you've been able to decrease your CO2 output by 5%. Okay, now the problem is, we have these articles, we have these. Literally 2 days ago, CO2 level just passes an important benchmark, a measure of humanity's war on nature. That was a headline, right? So cement companies realize we need to decrease our CO2 output even more. We need to improve our global warming potential even more. Okay, so if you take one thing from, I guess if you take two things from this presentation this morning, the cement industry needs to decrease its CO2 output and improve its global warming potential. That is what we're looking to do, right? So we have to abandon, for lack of a better word, we have to abandon ASTM C150. We've been using ASTM C150 for, I would say anyone who's on this call, when you were in school learning about concrete, you designed with ASTM C150. Your professors taught you with ASTM C150. If you started working, maybe designing with concrete, C150 is what you referenced. The person who mentored you used C150. Everyone, this was the document we used. Well, since it says 5%, we need to abandon that. And we need to go to what's called ASTM C595. And that's the standard specification for blended hydraulic cements. Now, why on earth would we use C595? Well, because that document, and boy, I'm clicking, it's awfully slow. That document says to make Portland limestone cement, so Portland limestone cement shall be a hydraulic cement in which the limestone content is more than 5%, but less than or equal to 15% by mass of the blended cement. So what C595 does, it allows you to go and use more limestone in that 1 ton of cement that you're going to market to the concrete producer. So like I said, for many years, we had 5% limestone. We want to reduce our CO2 output even more. So now we want to increase it past 5%. Well, guess what? We have to use this document, ASTM C595. So I hope that makes it clear why we're transitioning to C595. So when you look at C595, you're going to see some nomenclature changes, right? So forever we've been using a type 1 Portland cement, if you will. Well, according to ASTM C595, the nomenclature is now going to be type 1L, and then some parentheses, and you're going to have a value in there. Right now, I've got X there, where the X represents the amount of the targeted limestone. For example, a type 1L10. So this would be a type 1 limestone cement that has no more than 10% ground limestone in that 1 ton of Portland cement. Okay, makes sense? There's another document. It's called ASTM C1157. It's the standard spec for hydraulic cement. Now, in this document, there are no restrictions on the limestone addition. And, so there it's just called a type GU for general use. And I'm just making you aware of this because you may see this spec as well. But this one, again, has no limit. It just, says you can use in references as a GU. Now, if you look at C595, you're going to see some other cements in there. For example, you'll see a type 1S30. What is that? Well, that'd be a type 1 that has 30% slag cement blended into that 1 ton of cement. There's a type 1P5. What's that? Well, that would be a type 1 that has up to 5%. It might be like silica fume blended into that 1 ton of cement. And then you can blend several cementitious materials. You can have a 1T S30P5, and that would be 30% slag and maybe 4% silica fume, all blended into that 1 ton of cement. So the point is, these look kind of different, right? I mean, we're used to a type 1 and a type 3 or something like that. We need to kind of put our mind around some of this different nomenclature, and I can tell you, we've been building with these cements actually for many years, even here in Michigan, right? So again, why would a cement plant transition to ASTM C595? To lower the plant's global warming potential. We definitely got to have that down pat. And so transitioning from 5% limestone, which we've done for many years to make type 1, to less than 15% limestone to make a type 1L PLC, a plant will reduce its global warming potential. And I repeat that because, like I said, it's this is the thought process, if you will, to hopefully get us out of the crosshairs and get us out of these headlines that I read earlier. Okay. I mentioned some of these other cements. I can tell you that here's a picture of it's the M231 bypass in Holland and Grand Haven. I want to say that was probably built maybe 15 years ago or so, a dozen years ago. As I age, I think sometimes the years kind of blend together a little bit. But I can tell you that was made with a type 1T S25P4. Okay, and it's been built. It's been standing for many years, and it's probably a cement that you're probably not even really aware of. Here's the U of M big house, and this renovation was probably, I don't know, we were probably working on this maybe in like 2006 or so, and the bowl of the big house was built with a type 1T S25P5, and that was that long ago. So my point is, these aren't new materials. These are materials we've been using for many years, and they've proven the test of time, right? C595, the document, has proven that it's a good document. We can build with it. And I know what you're thinking. You're probably saying, well, let's face it, that's an MDOT job, and that's the big house. Well, I can show you. Here's a little house, and here's a driveway. This driveway was placed with a type 1S20, and I can tell you there's probably thousands upon thousands of driveways throughout at least Southeast Michigan that were placed with a type 1S20. I can't even imagine how many thousands of driveways went in with a type 1S20, since 2005. So my point is, the industry has been changing, and our specifications, we'll talk about that in a little bit, our designers need to to recognize this and get their specifications up to speed, and again, we really need to do this, and hopefully the first few slides kind of set the stage on why we need to be doing this. Okay, what about codes and standards and guides and things like that? One thing that you'll find is all of your cement specifications and codes recognize ASTM C595. whether it's the, you pick the building code, you pick the, AIA master spec, whatever document you want to pull up, you're most likely gonna, find that the cement industry, did its homework and, were properly cited along next to C-150. So type C-595 is as far as codes and so forth is considered as equal to C-150. For example, I've got here ACI 301. This is the specifications for structural concrete. And you can see here for cementitious materials, types, manufacturing, locations, shipping, so forth, shall be in compliance with ASTM C-150 and ASTM C-595. And then they even have down here C-1157, and that's why I kind of mentioned that as well. By the way, when you see ASTM and you see the letter M here, that just stands for metric. So that means you can buy the document, with English units or metric units, and that's kind of the idea there. But the point is, it's as simply as a comma and including C-595. So you'll see that in all the documents. I also include, I throw this in here, for example, this is the residential code. And I think a lot of folks sometimes, I don't know if they realize that there is a residential code, but you can see right here, cement shall conform to ASTM C-150, comma, C-595, or C-1157. So the point is, if there's any folks that get involved in residential concrete, you should have a copy of this document as well. But certainly you can see here that 595 is part of this document as well. So the question then would become, why would these codes and specifications allow a Portland limestone cement? Quite frankly, you may say, it sounds to me like you're putting sawdust in the hot dog, right? I mean, I told you a few minutes ago that instead of marketing 1 ton of Portland cement clinker, we're now going to take, up to 15% clinker out and put in up to 15% ground limestone. So you may say, how can this possibly work? My strengths are going to be lower. This is going to be, just horrible, because you're putting, like I said, you're putting sawdust in the hot dog. If you allow me to use that analogy. Well, the Portland Cement Association got together with, these are some big hitters here, if you will. We have Paul Tennis and Mike Thomas and Jason Weiss, and these are some of the folks that write all the important white papers and do all the important research and so forth. And I'm going to try to explain for you in probably a minute and a half or 2 minutes a pretty serious thesis they have on why ground limestone can work in that ton of cement that we are going to market to the concrete producer. So in a nutshell, they've determined there's basically 3 reasons why this works. 1 is the particle packing effect, 2 nucleation effects, and 3 chemical reactions. So instead of trying to, like I said, I'm going to do this in a minute and a half. What these gentlemen do in probably a 90-minute, well, I've actually sat in on some of their 90-minute presentations. But in a nutshell, particle packing, what are we talking about there? So I've got these 2 little cartoons, if you will. So this first cartoon, it's an idea of 100% cement. So this would be like a type 1 from many years ago, if you will, where we just had 100% Portland cement, and we would make concrete. Okay. Well, the idea we're introducing with the Portland cement line idea would be to fill in the voids, if you will, between the cement particles with this fine ground limestone. And so what happens there is, you're creating almost like a better skeletal system of the overall matrix, if that makes sense. So the skeletal system of the matrix is becoming denser, and with this we see some improvements, if you will, in the cement. For example, we would see you can have reduced water demand, and therefore water to cement ratios for equivalent workability are subsequently increased strengths. So the idea is this particle packing effect. It'd almost be kind of like using an intermediate aggregate, which I think Dan is going to talk about a little bit later. But the idea of this fine material creating a better matrix within our cement structure. Okay. Next is the idea of these nucleation sites. So what's going on there? Well, if you'll bear with me, we've got these two little cartoons that go from A to B, and this is our old system. We have these little cement particles here, and what happens as soon as we hit water onto cement, the cement is going to start to create it creates two things, but it's going to create the gel or the glue that's going to become like I said, the CSH, the calcium silicate hydrate. This is going to be the glue that's going to give us all the properties of the concrete that we want: our strength, our durability, our wear resistance, our this kind of thing. And so this glue, if you will, is this red here. Okay, so the idea is you hit the water with the cement onto the cement, and you start to create the glue in the paste, right? Well, if you look at then drawings C and D, what's happening there is in between these cement particles, we have these fine limestone particles. So then as the glue or the paste starts to be made, starts to occur, what happens is between those fine limestone particles, they allow the cement to go further, right? They kind of bridge the gap between cement particles, so your cement paste becomes more not economized, but it almost becomes a bridge between cement particles, right? So you get a better use of your cement glue, if you will. Your cement glue actually goes further because those tiny particles, bridge between cement particles and allow you to have a better overall matrix of paste in your concrete. So it's mainly these two ideas: the idea of particle packing and these nucleation effects that you're going to see in some data that I'm going to show you produce improved or even better result, or like for like or better results in concrete. So moving right along, I guess we have every cement company, we love to test. We have labs all over, and I know all cement companies do this or perform this type of testing. We're always benchmarking ourselves, looking at ourselves as compared to our competitors. For example, I can tell you at Wholesome, we were constantly grabbing our own product, but we obtain competitors' samples as well, and we have a mix. It's a mix that contains 564 pounds of cement. We use the same aggregate source. We use the same admixtures, the same lab personnel. And we're daily, generating mixes and benchmarking ourselves. Well, what's nice about this is we generate a lot of data, and so then we can kind of compare that data and kind of look and see, how we're doing. So what I'm getting at is what we did is when this is what Wholesome did, but I feel very confident that other cement companies and other cement plants did the same thing, at least the ones that are transitioning to a Portland limestone cement. So what we did is we said, well, we've got all this data. We have, we know what we produced in 2021 or are currently producing in 2021. So what we did is, I'm going to show you some graphs. And for example, you'll see some 3 dashed lines. The top dashed line is going to be the maximum for that particular study we did. The bottom will be the minimum for that study, and then the middle is pretty much like the average for that particular test that we performed. So then what we did, I grabbed a snapshot here. Well, I'll tell you, I try to be very transparent. I pulled, I think this was like July, August, September. So at our cement plants that wanted to transition, we would say, okay, make some type 1 PLC for for like a day, and then we'll test it and we'll see how it looks, and then we'll try it again next month. And the idea would be, you want to be able to, at a plant, you want to be able to produce something, but then you want it to be very uniform. So the idea is, yeah, you made it this month, can you make it next month? Oh, you made it those 2 months, can you make it a third and a fourth and a fifth? So you don't just flip the switch at a plant. You need to prove to yourself that, yes, you can do this. Yes, you can sustain it. Yes, you understand it, things like that. So this is some testing from product from, again, July, or was it, no, it was July, August, September. So, we ran some in, we slumped, for example, we hold all of our water at a constant 0.49 water cement ratio, which is, something that we do. And, we kind of then, evaluate how does it slump compared to what we made in 2021. And you can kind of see there, we were like, well, maybe we were at the low end, and we said, well, you need to make some improvements. Let's see if you can improve on slump, things like that. So that kind of gives you an idea of, where we were headed there. Concrete initial set. You can see again the dashed lines represent what we made last year or what we were making at the time last year, and then these grab samples, just kind of getting an idea of, hey, where do we fall, or do we like what we see, things like that. 1 day strength. You can see here we were again the dashed lines are what we were making literally last year, and the 1 day strength, we were like, yeah, seems like even though we're making this transition, yeah, the strengths seem to be there. So you may again say, well, how can those strengths be there? I mean, we were introducing more limestone fines. Well, again, it goes back to the idea of the particle packing, the nucleation sites. It's these principles you can see acting here, right? That it was these principles that are giving us the desirable 1 day strengths. Okay. 7 day, you made it in July, make it again. Okay, you made it in August, make it again. So these are the types of things we were doing at the plant. And then you can see there was our 28 days. And again, I just picked 3. I just picked 3 months in a row. So again, just kind of make a graph that was easy to look at, I suppose. But so as a cement company, once you do these types of things, and all cement companies do this. I mean, they or I suspect they do. I mean, it makes sense, and it's certainly being on top of your due diligence, right? Well, one thing that was kind of interesting is after we did this, or after we actually introduced this Portland limestone cement to the field. We have a customer in Ohio, and every 3 years, this particular customer, he takes his mixes and he generates 3-point curves, and but he generates his curves at a test lab. So what he does is he sends to the test lab all of his aggregate, all of his admixtures, all of his cementitious materials. And this test lab performs all of the work for him, right? so I asked him, well, you did that back in 2019, and he did it again this. I want to say it was probably around February or March, but this time he used the type 1L, the type 1L10, right? So I said, well, I'd like to see the data, and then I basically plotted the data. So you can see here again. This is not data from a cement company. This is done by an independent lab. But you can see here the type 1.2 is the red curve, and the type 1L10 is going to be the green curve. And he had a lot of mixes that he does. I just grabbed a few just for maybe a visual of what's kind of going on. And you can see here that the type 1L10 performed, what we've been telling people, it's going to be a like for like cement. And if they come back to me and say, well, it's performing better, well, then I certainly like hearing that. But I always say it's going to perform in a like for like nature. But here you can see it, performing well. Again, the type 1L, in this mix of his, performing very well over what we had in 2019. Here you can see probably a little bit closer for the like for like, but still kind of a I guess the leg up would be to the type 1L10. You may all those mixes I just showed you did not contain SCMs. So the use of SCMs such as fly ash or slag, how the type 1L PLC work with those, it's going to be very similar. And this is again our in-house testing. Just to give you an idea, we were pleased there. Now let's look at the field work. Again, work performed by an independent test lab. And you can see here, again, we're pretty satisfied. It's a like for like, if not better. Again, like for like, if not better, right? And then again, kind of lastly, here you can see this is a non-air train, 25% slag, 15% fly ash. And for all intents and purposes, certainly a like for like type product, okay? Okay, so that kind of gives you an idea of here we're trying to improve on our CO2 output. We're looking to improve on our cement performance. I think we've tried to establish that. So what can finishers see in finishability, for example, is that you can make a great cement, but if the person with the trowel doesn't like it, you've got problems there that are probably just as bad as some of the technical aspects of your cement. We do see about a 10% reduction in bleed. Well, I guess I got to be careful. This is I guess I'm talking as my product. We see a 10% reduction in bleed. However, it does appear creamier on the trowel. Okay, the bleed, for example, when we measure bleed in our lab, the type 1L10, we measured 29 milliliters of bleed water, where the old type 1 would bleed 32 milliliters of bleed water. So approximately a 10% reduction. But what's interesting is like I said, it certainly appears creamier on the trowel. And what I think is going on is, sometimes I depending on weather, some people may say, well, it seems a little sticky or something like that. I think what's really going on there is the fact that there's a little bit of a reduction in bleed. And I think that reduction in bleed is some people may see that as, it's sticky or something. I guess what I would say is, we've been talking to the concrete base, and the idea is, we may need, you can't just swap it in a like for like manner. It's going to perform like for like, but we may need to adjust air a little bit. and and there is a relationship between air and water. And it's not going to be great. It'll be, I would say, depending on the chemicals you use, it might be 0 to 5%, maybe even a 3 to 5%, change in some of your chemical dosage, right? So those are things that you'll certainly want to be aware of. Color, for example, it's extremely close. This is probably the most severe way to look at color. This is we put the cement down on a table. We take a piece of glass and we put the glass over the two cements, and then observe them. And even though this is a picture, I can tell you that it's very, very, very similar, very close in color. So what about specifications in the design community? This is a kind of a tough one. I can tell you that we've been talking about making this transition for a number of years, actually. And I think one of the concerns was the design community. What are we going to do with the design community? Are all the technical people going to be spending, every minute of every day on the phone with designers, trying to, educate them on what it is we're doing? And I can tell you, here in Michigan, like I said, Alpina transitioned basically January 1. And since then, I've been on 5 conference calls since January 1. To me, that's not being overworked at all. Okay. And here's an example. I got this specification from a customer of ours. He sent it to me in January. And he says, what am I going to do? Because you can see right here, it says Portland Cement, and there's no C595. What do I do? The simple answer, when you talk to the designer, is you put a comma right next to that C150M, and you write C595. It's I've shown you in the codes how the codes handled it, and it can be handled as simply in your specifications. Now, of course, there's going to be specifications out there that don't recognize this. I can tell you this particular one. It wasn't even a conference call. I spoke to the designer. We were on the phone. I'll bet you we were on the phone 20 minutes, and I'll bet you 15 of those minutes we kind of talked about things unrelated to the specification. I want to say in the first 5 minutes, I spoke to him about CO2. I spoke to him about the Clean Future Act. I spoke to him about the idea between the nucleation sites, the particle packing, and believe it or not, I was able to get that in. Like I said, it was pretty quick. And he said, tell this producer to send their submittal through, and they aren't going to have any problem. So it has been, like I said, it has been surprisingly positive from the design community. It really has. So I guess what I would say is, does the design community needs to get its specifications, out of the 1970s. And, I know we do a lot of cut and paste. I get it. But the reality is we need to get our specs up to speed. And I showed you earlier that we've been building with C595, and I showed you, real world examples here in Michigan dating back to 2005. So it's been around, it's been there, and so that's what we need. We really need to recognize this. There are going to be, the changes are extremely minor. For the sake of time, I won't get too much into this, but for example, the specific gravity, I would say, is going to be lower. So regardless of whoever's cement you're designing with, 3.15 probably isn't the number. I can tell you the Alpina is going to be 3.10. You'd want to check with your specific your individual supplier, but and we're talking this is more of a this is a very small change, and it's going to change their mix design very, very little, but it's certainly something you're going to want to be aware of, right? mill test reports, they're going to change. You can see here on the left is an example of a mill test report. It's got a lot more data than the example on the right, which is the blended cement. With respect to these mill test reports, what I can tell you here is, well, I can only speak for my company, but we report what is mandated by ASTM. So that's why ASTM tells us to put this information down. So this is what we have. If you're interested in a constituent of the cement that you do not see, but you used to see last year on the old report, by all means, ask your supplier, put the question through, and I can tell you, I'm sure every cement company is more than happy to, we all want to be very transparent. We all want to make sure you're aware of what's the cement is, and we're all more than happy to, provide you that information. I think Dan's going to touch on MDOT, but it's just part of my presentation, so I can tell you that, all of the DOTs in the Great Lakes area here are all on board with this change. I can tell you that MDOT has been outstanding. I don't know if there's any MDOT folks on the call, but I can tell you that the Michigan Concrete Association, Dan and his team, they have an outstanding relationship with MDOT. And as this work was coming through, and I mean, a lot of this work was right before the holidays, kind of a thing, and there was a lot of midnight oil being burned to figure out how to convey this change. Even though MDOT recognized this in some special provisions, years ago. When the cement companies went to MDOT and said, "Hey, we're flipping the switch January 1," MDOT really worked well and put together some documents that I think they're quick, they're easy to read. They spell out very clearly what someone needs to do to use Portland limestone cement. They have a field guide and they have a special provision. And you can see here, you can see the date 12/16/21. So as I mentioned, there was a lot of midnight oil being burned late in the year when I think a lot of folks were, like I said, probably thinking about fun stuff. I can tell you that the MCA and MDOT were really working hard on trying to make this a smooth transition. I want to give you some thoughts from what MDOT has put in these documents. So if you'll forgive me, you can see it says published national research supports findings that the fresh and hardened properties of concrete produced using type 1L Portland cement are like those of normal type 1. And you're going to find that in the field guide. Further, there is added evidence that type 1L Portland cement may contribute toward improved durability for concrete exposed to harsh environmental conditions, again in their field guide. And then lastly, the contractor may substitute type 1L Portland cement in lieu of type 1 Portland cement for concrete mixtures and other applications where type 1 Portland cement is specified, provided documentation showing specification compliance as described herein. So again, kudos to MDOT for putting some documentation together that is easy to read and quite frankly, pretty easy to follow and extremely very reasonable in their approach. So if you deal with MDOT, by all means, check that out. So this is the part of the presentation where I'm supposed to show you some pretty slides that show you, trust me, we have history with Portland limestone cement. Many buildings in Seattle. Here's some road work in paving in Oklahoma City. A stadium renovation. A children's hospital, So what's interesting, you'll notice a lot of these completed projects are in those yellow states that, like I told you, they had to transition years ago because the legislation in those states was kind of encouraging it, if you will. So kind of lastly, or kind of bringing it home here, here's an example where the Gordie Howe Bridge, which is currently under construction, it started in 2019 with an ASTMC 595 type 1P13. Okay. And this year it's going to transition to an ASTMC 595 type 1T L9 P13. So my point is, yeah, some different numbers. We certainly got to put our mind around these numbers, but certainly nomenclature, I should say, but it's certainly very, very real. So in conclusion, it's the responsibility of the cement and concrete industry to address the current climate situation. And again, the headlines are literally from this week's news. Cement companies have taken steps to reduce the CO2 output in the manufacturing process at their plants. Hopefully you understand, how and why. One of the greatest ways to reduce CO2 emissions is by eliminating the production of ASTMC 150 type 1 and replacing it with an ASTMC 595 type 1L Portland limestone cement. Type 1L PLC is an engineered product and as a standard of the industry is specified and considered as equal to type 1. And hopefully from the data I've shown you, you would agree. Type 1L PLC is acknowledged and accepted for use wherever type 1 is specified or cited in all specifications, codes, standards, and guides. To summarize, responsible governments, owners, specifiers, and consumers all demand type 1L PLC. So I tried to keep it to an hour. I think we started about 5 after, and I got about 5 after. So I hope it all made sense. And so Heather, I don't know if you had questions or you want to do those in the end.
Thank you, Claude. We do have a couple questions in the chat, and then Dan's got a few things that he'll summarize with. The questions are, how does the change to PLC impact the cost of cement production for the plant?
How does, yeah, so, no, I don't think any companies are going to divulge, what their costs are. I can tell you costs are extremely high due to inflation. So the cost of cement is just to produce it is just astronomical, really. So even though you may say, oh, you guys are putting ground limestone as opposed to clinker, I promise you that the costs of producing cement is just like anything. It is greatly on the rise. So if anything, I guess I would say I've shown you through test data that we've improved the cement. And so if anything, from a cost standpoint, you should be seeing and enjoying an improvement in the cement more than a detriment.
Okay, thank you. The next question we have is, why has ASTM C150 been so widely applied if C595 is also permissible?
Yeah, so I guess the answer to that would be because everybody was producing an ASTM type 1, and the C595 cements that I showed you, those are specialty blended cements, and there's to make a specialty blended cement, it's not something that all cement companies can do.
Got it. Okay, what has been the reaction of the concrete producers to the use of PLC? Have there been any availability or production related issues?
No, I am not aware of any production related issues or availability issues. Again, I can only speak for Wholesome. We flipped the switch, if you will, January 1. And it's readily available. No, let me rephrase that. It is the only cement available since this is the MCA, I'll say it is the only cement available from Wholesome in the state of Michigan.
Okay, I'm going to ask one last question and then we'll answer the other one. Dan, I think, might answer the other one as we go, but what is the particle sizing of the crushed limestone portion of the PLC? Being
Yeah,
really
that's good. But
other particles.
yeah, that's a good point. So I don't have that, and I can get that. So I guess what I would say is it's the PSD of the ground limestone. I guess I can pull that information. If you want to give me that person's name, I'd be happy to get that information to them. But that's a great question.
Okay,
I guess I would say the Blaine, let me say this much. The Blaine of the type 1 PLC versus the type 1 is approximately like 14% finer. Okay. So the overall Blaine, the overall Blaine of the type 1L PLC is finer than that of type 1. But this person asked specifically of the
particle sizing.
yeah, so that I'd have to get.
I'll put Claude's information in the chat. The person who asked that question, if you can email Claude, I'm sure he can get you that information. I'm going to stop questions for a second here. Again, this webinar is being recorded, will be posted on our MCA page, which I will also put in the chat to everyone, that, or at least email it out, that all of this information will be included on our PLC page. And with that, I'm going to let Dan DeGraff take over and bring us home. Thank you.
Heather, can you see my screen now?
Yep, we can see your screen.
All right. All right. And we're going to bring this back from cement to the world of concrete, because we're working with concrete, and we're also trying to be in the real world here too. But just one of the things to kind of reemphasize this whole idea of the CO2 and the energy that's tied up in our building products. Concrete is always on the low end of the scale. It is the most efficient building product we can use. If we start using glass, timber, clays, plastics, are all much higher. As Claude said, we're the second most used product in the world. That's why we have a big target on our back. But it's hard to find things that are much more sustainable as far as a building product than what we have in concrete. I'm going to go through a few things, and we're going to talk about reduced carbon mixes, trying to get back to Arnold to show him that we are already doing what he thought was not being done. So, but there are things that we have to pay attention to as we make things with this new concrete mixes, and areas that what we need to do to work in this new environment that we are all now faced with. Claude, they talked about what's happening, but it is real. On March 17th, General Services Administration published a new maximum global warming potential guide. And so in a 6-SAC mix, the answer is you got to be under 300. And that is their CO2 per kilogram cubic meter. And you'll see some variation here, but type 1 cement, most of the country is averaging about 0.9. I think Claude said a pound for pound, but it's that all varies depending on what the burner fuels are going into the plants. But type 1 cement and the clinker has this 0.9 to 1 ton. Here's the one formula I'll give you today. Kilogram per cubic meter equals 1.68 pounds per cubic yard. That's our conversion from English to metric. Now, what's that really mean? And this is basically answering Arnold. If we took a standard 6-SAC mix with type 1 cement, we're going to be right around 301 on the global warming potential. If we just switched to a type 1L cement, we would reduce that amount by 10%. So that's a straight 10% reduction. In Michigan, since early 2000s, we've been working with well-graded aggregates, taking out some of the cement paste reducing the total cement content. That alone, if we just stayed with type 1, is reducing our carbon footprint by 11%. With the type 1L, it's dropping it by 20%. The other thing we've been using very religiously is supplemental cements, fly ashes and slag cements. With a 30% replacement of slag cement, there's a 30% reduction in global warming potential, right? If we use the type 1L in conjunction with that, it's a 37%. So net combined today, we are making concrete in Michigan that's 44% lower in global warming potential than we did 20 years ago. We are already doing what Arnold said that he thought the Europeans were doing. He should have just come to Europe, okay? We have good beer in Michigan. They can come to Michigan to see the same thing they went to Europe for. But and as Claude said, how do you specify it? It's under C595. That's the simple answer. It is not a C150 cement anymore, but the product is produced, it's manufactured to react and behave like type 1 as far as most of the set requirements that you've seen. What did we do with MDOT? And Claude is right. We partnered with MDOT. MDOT actually had the type 1L cement allowed in mixes since 2008 or 9 is when we first, maybe even 2010 was maybe we put it in the specifications. We just had to wait until the cement producers made it. With the demand we have and the production we have for cement in this state, we do not have the ability to have two products. It's the silo capacity of the cement producers, the shipment capacity, and also the producer and the ready mix producers and the concrete pavers. Their silo capacity of their plants are such that we only have room for one product in this line. So it's an all or nothing type system if we're going to meet any kind of the demand that's out there. But what happened last November, basically it was the middle of October last year, when the cement companies came and said, we've decided that January 1 is our day. We had to face reality. How are we going to handle the mixes that are out there? Most mixes that MDOT has are good for 2 years. There are projects that are continuing. So we put this special provision together, worked closely with John Staten at MDOT and Tim Stallard. But anyway, the bottom line is this special provision's out there. It can be incorporated in jobs from either the 2012 spec book or the 2020 spec book. But it basically says contractors may substitute type 1L cement in lieu of type 1. And it does require that the concrete producer produce 4-yard minimum trial batch of one mix that they've been using. We wanted the producers to actually have some experience with this product before it goes out on the street. And they needed to test the fresh properties with a 7-day break. They need to have some experience with it before it was shipped to the job. But once they did it for one mix, then that plant is good for all of the mixes that they produce. See, for all approved concrete mixtures generated at the concrete production facility for the project. So once they do one trial batch, they're good for making that 1-for-1 switch on all of their materials. Couple caveats. Once a project is switched, you don't go back. And like Claude said, you can't buy it anymore. I do know that the bagged cement business, where you go to the supply houses or Lowe's or Home Depot, all of the cement that's now being supplied is a type 1L cement, and those as well. And the other requirement that we put in the spec was that you have to, the job mix formula and all the sublots have to be, you don't want to mix type 1 with type 1L in a sublot. So on the project sites, the day they switched, they had to close out any existing sublots and start over with a new lot. There is no additional laboratory trial batch requirements other than doing the 4-yard batch. Now, some of the pavers have elected to do a mixed design, and they're just going to run a new mixed design with a type 1L cement, which has been allowed for quite a while. And so this is how the specification is now set up to work. Talk about long-term performance. I don't know if many of you are aware, but Turney Consulting Group out of Kalamazoo is a very high-tech testing firm, and they get involved in pretty high-level stuff around the country. There was a project in Oregon similar to the Gordie Howe Bridge, and they were like Gordie Howe Bridge. They wanted to have a 100-year design service life of concrete. So they came to Turney Consulting Group and said, run some tests to show us that our type 1L cement will be a 100-year service life concrete. And they did that. And in those cases out there, they're using a type F fly ash, but their results showed that the type 1L cement was going to perform probably slightly a little better than the type 1 would have. So they've confirmed with their testing that long-term, we should expect to see very good performance with this type 1L cement. Now, as we go into reduced carbon mixes, some of the steps that we will be taking and we need to take and follow the lead of what we've been doing with MDOT for many years, but the well-graded aggregates, which is a uniform blend of all size of aggregates. It does make it much easier for the material to get moved around because we're not rolling rocks over the top of other big rocks. There's a bunch of other small blocks that we put in place. It's like driving over a curb with your car. Driving over a 6-inch curb isn't easy, but if you had a 2x4 block that's set there, it would be much easier for your car to drive over. So small rocks fill up the holes. We don't need as much cement paste. We're reducing our CO2. And by the way, aggregates are much stronger than our cement paste, right? That's a given. So with a well-graded single-size material, you need a lot of paste to fill in all the gaps. Poorly graded, you still need a fair amount of grout. But when we get to well-graded, we just don't need as much glue. And we eliminate glue, we eliminate CO2, we make ourselves more environmentally friendly. And we have a mix that works much better. Here's a couple pictures. The one on the left was the standard gap graded mixes with a lot of sand and grout versus the well-graded mixes where we've added these smaller aggregate chips. Our strength, when we took a standard P mix from MDOT, we went from a specified 3,500 mix that actually reached usually around 4,500 PSI. Once we went to well-graded, I think our brakes are now around 5,500 PSI. So we gained quite a bit of strength by just relying on the aggregates. And at the same time, we took another half a sack of cement out of our mix designs. So the other big step to take is the utilization of supplemental cements. It's fly ash, which is becoming harder to find, but the slag cement supply in Michigan right now is pretty sound, and we're relying on that. But one of the things that when you use supplemental cements, you will find that you will gain significant strength between age 28 and 90 days. With some of the type 1 cements, once you got the 28 days, there wasn't much bump between 28 and 90. But what this tells you is that reaction with the supplemental cements is ongoing for a much longer period of time. The mix doesn't set up quite as fast. It's easier to work with. But we get some really good long-term durability if we allow it to fully gain this internal strength that really locks it together. And the 28-day strengths were always, we're getting to what we need for stripping and opening to traffic. in many cases, we're getting open to traffic strength in Michigan with our paving mixes in less than 24 hours. But this densification, this waterproofing of our concrete is something that the supplemental cements do for us, and that happens over a longer period of time. Snow is coming sometime. Took this picture over at the Michigan State campus a few years ago, but they were spraying the salt brines down on their campus because they knew it was going to snow. And this was probably 3 or 4 days after the last snowstorm, but you can see right where they put that brine because that brine is still pulling water into that concrete. So our biggest issue with concrete, exterior concrete in Michigan, is this salt attack that's really intensifies the way we've done it in the last few years by using all these brines. When we used to throw rock salt down, they'd hit, and they'd land, they'd melt a little snow, and then they'd bounce off. Nowadays, we're putting it on at such concentrated levels. So we have to make our concrete waterproof. We have to make it permanently dense. And that's what the supplemental cements really help us with. Temperature control. With the supplemental cements, maybe not so much as adding the type 1L, but with the supplemental cements, mixed temperature is much more critical. Above 70 degrees, our concrete's going to set up and perform like we normally expect it to. And on hot summer days, we're never going to usually get to 90. But if we pour concrete out at 50-degree weather with 50-degree mixed temperatures, it's going to lay there quite a bit longer in the fall or in the spring before it sets up enough. And so it's important that we get our mixed temperature right, be very much more cognizant of the mixed temperature with these low carbon mixes. And by the way, curing is a huge deal. We have to keep that water in longer so that reaction can continue to take place. So a couple of things on saw time. In the summer, the ground is warm, the concrete surface is warm, the concrete sets from the surface down. Ideal conditions for sawing joints, right? The top of the concrete's going to get hard fast, and we can saw the joints, and then we're in good shape. But in the fall, the ground is still warm while the air temperature really cools off at night. With the surface temperature of your concrete being cool, the concrete may actually start setting from the ground up, creating a saw window issue. That's another place where heating the concrete up so it reacts more consistently will help us through some of this. And in the spring, we have the condition where the ground is cold, the concrete materials are cold, set will likely be delayed. Heating the concrete will help get it kick-started. But once you pour it on the ground in the spring, if it's cool air, it just sets much slower, and we're subject to any vibrations or any other things that could impact that concrete. Some proper placement practices. When we start using well-graded mixes with supplementals, we don't need extra water, but if you would look at that concrete, it just looks drier. And the first thing everybody wants to do is add water. We don't need to add water, but we do need to vibrate. Once you hit that with a vibrator, it will come very much alive and go right into the place where we want it. We also want to keep pushing hard to keep all the water to be added at the plant, not on the grade. If we're always adding water to a mixer truck, we're not doing ourselves well. There's a habit of producers to hold back water just so the contractor can add some on site. We need to break that cycle. These mixes have the right amount of water they need. They behave nicely as long as we're living within those proper zones. Curing. We want to talk about curing a little bit. We need to apply this curing compound immediately. This seals the water in. You almost can't seal it too soon. Claude noted that the bleed water is being reduced. So we need to keep that water there so we can fully hydrate our mixes. We got to have a complete coverage. You know, if it's white, the surface should look like a clean sheet of paper. If it's blotchy, you know, we tell people if they were painting your house and it came out looking blotchy, what would you tell the painter to do? And that is to go back and repaint it. It does need to be a complete coverage. You know, like I said, supplemental cements are secondary reacting cements. They must still have water available for several days. We cannot let that surface dry out in that first few hours. There's a good picture of a guy, even with a reaching all the way across, you can see that slab is a nice coating. It's a very complete coverage, not blotchy. That's what we're looking for. We also talk about sealers, and that's something that we need to consider a little more than we have in the past. You can buy a paint, which is, you know, marthaculate, waxes, acrylics, chip seals. We can paint a surface, that'll seal it. Pore blockers. These are these pore blockers are chemicals that we put on that react with the calcium hydroxide that's in our concrete and form a gel that blocks moisture. But this also, it's basically caps it keeps the moisture in, and it won't let moisture leave or won't let moisture in. Some of the products you've heard of are lithium-based materials or linseed oil, the old boiled linseed oil that we used to put on bridge decks in the past, kind of a pore blocker type. And nowadays we also have some chemically reactive sealers. They're water repellents. They react with a silica to form a permanent attached water molecule. So it basically keeps that water and the salt later on that comes from getting into our concrete. Those are the salines and siloxanes you've heard about. When do you apply a sealer? You know, the right time to put a sealer on, they don't really consider them curing membranes, but they should be applied to hardened concrete after about 28 days. But they keep the water and the salt out. The supplemental cements provide great long-term density as long as the reaction is allowed to be completed. But we built a lot of projects in the fall, and at the end of that fall, the true density hasn't been reached yet. It's strong enough to handle the traffic loading, but it's not impermeable. It hasn't sealed itself up enough, so it's a long-term seal-proof material. So we really are pushing people to think about adding some sealers in the fall on all the new flat work prior to that first winter. We put a silane sealer down. It doesn't cost much, but it will give you that protection, and it'll keep these driveways that we see starting after that first winter. But especially your exterior flat work and any commercial work outside buildings where we know we throw a lot of salt down, it's pretty cheap insurance to keep that concrete waterproof. So silanes are extremely small. It penetrates the surface, so you spray a silane down and it'll look like it didn't do anything. But it soaks right into that concrete and reacts internally. It doesn't change your skid or slip resistance, and it really works better for a direct application on concrete. Siloxanes are slightly larger. They do form a hydrophobic resin, but they're really great for concrete block, non-cementitious material like brick, stucco, kind of like exterior or vertical walls. But silanes are really something we need to think about, at least before that first winter. By the time the second winter rolls around, our SCMs have reacted, and we have a nice, very dense mix that will perform well. So just as a little bit of a wrap up, we are either myself, Steve Walkus, Heather Smith, are all available for contacts for any questions. And we hope you found this seminar to be helpful. And I guess, Heather, where are we at on questions?
We just have a few here. I know we went a little over the time limit. We'll give you the extra for your continuing education hours. But the questions we have, let's see. Due to the characteristics or qualities of C595 affecting concrete curing, vapor transmission, or the installation of finished materials, I believe Dan answered that in his presentation. Is there anything you, Dan or Claude, would like to add to that?
I didn't fully get that, but I would say, you know, the importance of curing just can't be, you know, stressed the most. Yeah.
Okay, it's basically, it reacts very similarly to these, it reacts the same as type 1. I think that's really the question there, but curing is just as essential. The next question is it possible or practical to capture the CO2 produced rather than trying to prevent CO2 production on the front end of the cement production process?
Yeah, that, you know, so my company, I can only really speak for my company. That's an interesting question, and that's something that we are looking at very closely. It actually was made the news a number of months ago, because we're working with a company to investigate that further. In the idea at the cement plant that we're finding, though, is, you know, you would almost have to build, you know, just for the sake of discussion, like a nuclear power plant right next to the cement plant to do that, to capture that. So the technology is just, you know, it's such in its infancy that to do that, boy, it's you know, it's, yeah, the thought process is there, but like I said, you would be building such a huge plant to basically do that. It's kind of, right now, the better way to go is a PLC cement.
Okay, is there an increase in crushing operations at the mine to produce the smaller quote unquote chips needed for a well-graded aggregate? If so, what is the increased carbon output of that operation? Does it offset the reduction in paste as far as CO2 is concerned?
You know, as part of the crushing process, aggregates are broken up. I think one of the things that we always compete with other industries for the smaller chips. Asphalt tries to run well-graded mixes, and so they like the smaller chips. But we both realize that well-graded mixes are much more stable. We can, you know, the ride quality gets improved when you have well-graded mixes as well, some other benefits. What I guess the added expense would be you're handling a third aggregate typically, which means you have 3 stockpiles instead of 2 stockpiles. It gets a little bit, you are bringing in those other materials, but as far as the crushing operation, I think those chips are kind of manufactured as you make any rock. And in the past, what they've done is screened off those materials and used them in other locations. And what we're saying now is we need those back. So it's not, the crushing doesn't change that much, but the product handling does change a little bit, but it is worth it for many benefits besides the CO2.
Okay, what type of time frame should we be recommending for floor flatness testing, given the changing set times that were indicated, Claude?
Boy, I hope, I don't know if I showed set time, but I guess what I'm getting at, we tried to design this. Well, I think you know, cement companies designed it to be a like for like cement. So, you know, you shouldn't see something that's so drastic that you need to change, you know, change those numbers. So, you know, it's going to perform more in a like for like manner. Like I said, you know, maybe a little less bleed kind of thing, 10% less bleed, you know, that kind of stuff. But I think, you know, when you're talking about F numbers and things, you should consider it a like for like with whatever you were doing last year.
Okay.
I'd let me add one thing to that. With well-graded materials, we're reducing the cement content. When we look at floor flatness and things, we're looking for curl and warp issues. That's caused by shrinkage. And if you have less cement and more aggregate on aggregate, you have less shrinkage. So I think the benefits of the well-graded probably offset any fears of any longer term shrinkage effects. It will take a little longer for the water to leave a well-graded SCM mix, but we're talking a minor blip on the overall net scale. But because we've eliminated a big amount of the cement product in the paste and replaced it with aggregates that don't shrink, I think we probably minimized a lot of that shrinkage that we used to be worried about.
Okay, the last question that we have is, does PLC change the cement content that will accept color for integral color, or will it still be the 564 pounds of cementitious material to color for decorative? I believe it's still the same, Claude.
Yeah, I would say like for like. Hopefully you saw in that, and I know it was just a photograph, but you know, I tell you, water cement ratio is going to play a bigger, you know, aspect on color than a type 1 PLC.
Okay, and I would just say work with the decorative color producer if you have any questions on that. With that, I know we've gone over time. I am going to close us up here. We will send out professional development hour certificates to everyone who stayed on. I get a report of who stayed on for this, so we will send those out. Again, this will be also listed on our website, miconcrete.org/Portland-limestone-cement. It's also linked on our homepage. And I'll get Claude's slides, and we will also link the slides up there on that page as well, so you can share them with your offices or anyone else you need to do that with. Again, I put our contact information in the chat, so I'll leave it up for a minute so you can get that written down. And thank you to Claude and to Dan for a great presentation today, and thank you to everyone who attended. We appreciate it, and have a good rest of your day.
Great, thanks.
Thanks a lot.
Thanks, guys. See ya.